Okay, so question number 3 is asking, show that phenol is more acidic than cyclohexanol. So I think they're the same thing. Yeah. I don't think I know. How do you draw that? How do you draw phenol? Look that up real quick. On the functional table. Okay, so yeah. I don't really use this. I usually use pen and paper, but yeah. Phenol has an OH right here. Yeah, it's the same thing. Oh, but there's one difference. This has, and I'm guessing cyclohexanol, whatever, doesn't. This is phenol. And this is cyclohexyl. Cyclohexyl versus. Okay, so they're asking for which one is more acidic. So we just base the reasoning is between size, electronegativity, and resonance. But we don't do it on this. We do it on the, what do you call it? The conjugate. We do it on the conjugate. So let me do that real quick. Okay. Let's see. So before, it would have been like, before the conjugate, this is like, actually, don't forget I said anything about the conjugate. For right now, this is what it looks like when you draw it out. And exact same thing without the double bond all over, making it a ring. There's no ring. This is what it looks like. Okay, sorry, I messed that up. Okay, so when you take the conjugate, you just take an H out. Simple. Take an H out. Take an H out. Okay, and then oxygen needs to follow the octet rule. So lone pair right here. Lone pair right here. And this is negative. If you want to know why it's negative, it just is. No, I'm just kidding. So the reason why it's negative is the formula is valence electrons minus bonds minus dots. So oxygen has about 6 valence electrons and 1 bond and 6 dots. So 6 valence electrons is, you know what? Let me draw it out for you. 6. This is valence electrons. And how many bonds? 1 bond. How many dots? 6 dots. So 6 minus 1 is 5. What's 5 minus 6? Negative 1. So that's negative 1 equals negative 1. They're both negative 1. That's the reasoning behind it. Okay. So this is the conjugate right here. Conjugate base. Conjugate base. Okay. Let's see. You want to move this lone pair? Actually, I'm getting ahead of myself. So we're gonna look at 3 things: size, electronegativity, and resonance. We'll start with resonance because get the hard stuff out of the way. So let's look at let's look at this one first. The, what do you call it? Phenol, whatever. You need a pi bond and a lone pair. This is the lone pair. This is the pi bond. So we can make a resonance structure, actually. 1, 2, 3. This moves right here. Okay? And it becomes... Well, I'll show you what it becomes later. And then this other bond, it goes right here. Alright? So that's one resonance. And, okay. Let me redraw that real quick. Sorry, I know my handwriting is terrible. I suck at drawing. Oxygen. 1, 2, 3, 4. Wait. Sorry. This doesn't belong here. Because remember how I said we take it out? So a lone pair comes right here. This becomes negative right here. This is a negative. Okay? That's one resonance structure. I see one more. There is a pi bond right here. Lone pair right here. So 1, 2, 3. This moves right here. And this moves right here. Let me show you what that looks like. God, I'm so bad at drawing on here, it's not even funny. One, 2, 3, 4. Let's see. This becomes a double bond. God damn it. Excuse my language. And this becomes and this becomes a lone pair. So the negative charge is right here, but now it is right here. I did not finish the structure. Let me do that. Okay. I think that was it. Yeah. So wait. Messed up here somewhere. Nope, I got it right. Okay. So just do it again. Same exact thing. Look, I could go back here and do a resonance here, but I can't do that. The reason being, it'll just take you back to the original structure. You want to keep moving forward when working with the resonance. 1, 2, 3. I actually just learned this today, so surprised I got this far. Yeah, so this goes right here, makes a double bond, and this goes right here. It makes a, lone pair. Let me make that real quick. So much drawing. It's all worth it for that 7.5. Okay. Yeah, so yeah. Okay. So this becomes negative now. Reason being, the lone pair is right here. Just take that negative sign wherever you take the lone pair. That's my thing. Yeah, that's it. You are out of resonance. So if you look back at it, 1, 2, 3, 4. There are 4 resonants, meaning 4 formal charges. 4 resonance. Okay. Now let's look at the cyclo-oxyl, whatever you want to call it. So I don't even see a double bond. So no resonance. Easy dub. But apparently you still have to look at the size and electronegativity. So size of the oxygen, if you look on the periodic table, the size of oxygen versus the size of oxygen is actually the same. Prepare to have your mind blown. It's the same because it's the same element and it's the same electronegativity. So you can't really look at either of those. You have to look at the resonance. So let me write that down. Size and electronegativity is the same for both. So you can't look at size and electronegativity for either of them. What you have to look at is the resonance. And this has no resonance. And this has 4 resonance structures. So this phenol is the obvious winner. Okay, what else? What else can I do? What else can I... This is my analysis right here. What else do I have to do? Let me look at the question. So, at the end, the answer is phenol is more acidic, right? Yeah, acidic. Not unstable. I was thinking of something else. Due to the fact that it has 4 charges, because we found that out from the resonance structures, right? This is the answer. Thanks for watching. Okay, let me make sure this is recording. Alright, so question number 2 is asking to draw a name for constitutional isomers of C4H7Br. One should have a complicated substitution included in the alkane. Okay, let me draw that real quick. 1, 2, 3. Okay. 4 carbons. And this is bromide. Okay. Actually, this is a very bad picture. Let me think. Okay, I think I got something. So another way to draw this would be with a double bond. Put the double bond. You put it right here. And then the BR could be right. Actually, you know what? Let me make the BR right here. So you have 1, 2, 3, 4 carbons, 1 bromine. Okay. So So now they're asking for the isomers. The name of this would be, let me start off with the name. So this is it's a carbon chain with a branch on two. Could be 1, 2, 3, 4, or 1, 2, 3. It's obviously going to be 1, 2, 3, 4 because you don't want the bromo on 3. So let me get this. Okay. 2 bromo, 2 bromo, butane. Because butane is due to the 4. That's the name. Okay. Now where else could I place this bromide? That's going to be the isomer without it changing its form. I could place it on, I can't place it on the second branch. I can't place it on the third branch because that's the same thing. I guess I could I think. I could just make it part of the thing. So these are all carbons. And this is bromide. And the name for this would be, well, we're going to look at it from the other way. So this would be 1, because we want the smallest branch. Whatever, 4. Well, actually, no, this is not 1. This is 1. This. Yeah. Well, no, that is 1. But whatever. I had it right. So the name of this would be 1-bromobutane because it's on the first branch. Sorry, I got this. 1, 2, 3, 4. On the first branch, on the first one, you have this branch. This is a branch. And then on the branch, you have bromo. So for that reason, it's called 1-bromobutane. What else I got? Let me think. Maybe I could do something like this. See? Because we have, what, 4 carbons. I feel isomers on the test. Actually, sorry. I think I got something. For this, you just have to come up with things randomly. Like, where can I put it? So I don't like this question. So you can put a bromine right here. And instead, 1, 2, 3. Instead of a carbon right here, whoops. Instead of a carbon right here, I could maybe put like a carbon right here. But yeah, I could do that. And it would be bromo comes first before methyl, so you want, yeah, you want that. No, wait. Yeah, that makes sense. Actually, does it make sense? Sorry, I kind of did this wrong. Okay. Like that. And then like that. No way, because that would not be the longest carbon chain. So 1 bromo, 2 methyl propane. 1 bromo, 2 ethyl, 2 methyl, sorry. 1 bromo, 2 methyl propane. Okay, that works. 2 bromo butane, 1 bromo butane. What else could I do? So I have, let me try I can make another one with just 3, with the propane. 1, 2, 3. Okay, let's see. Maybe I can put like a bromo right here, because I don't want it on 1 or 3 because it's the same thing as the last one. Bromo. This is tough, man. I could maybe just put like a methyl right here. So 1. No, wait, that would make no sense. I need it. That makes no sense. Because I need the bromide first anyways. It's the same thing as the last one. Shit. Maybe I can just put it right on top. That might work. One bromo, 1 methyl. Nah, that makes no sense. I'm just pulling stuff. I don't know. Whatever works. Let's see. I think I could do. Actually, I guess that would work. Because one, you don't have to start from furthest to the right. Yeah, this would work. 2 bromo 2 methyl, because you're on whatever way you look at it. 1, 2, 1, 2, doesn't matter. Same shit. Same thing. Propane. Okay. This is like, we're at propane right now. If you go any lower to ethyl, it's just gonna repeat the. You're gonna have to find the longest carbon chain. It's just a repeat of these. So I think there's only 4. This is the answer. These are all the constitutional isomers. This one, 1 bromobutane, 2 bromobutane, 1 bromo, 2 methyl propane, 2 bromo, 2 methyl propane. Propane. That's the answer. Okay. So the question for number 1 is asking, find an organic compound with 3 or functional groups that must contain an oxygen containing functional group, nitrogen containing functional group, and 1 other functional group, and name them. Also, for every atom in the structure, identify each atom's electron geometry, molecular geometry, and hybridization. Okay, so this, I just chose this structure, Capsine, is that if that's how you call it, and I think this fits the requirements. Okay. So what I'm gonna do first, I'm going to draw out the H3C, CH3s on the right side, both the CH3s. So first I'm gonna take this out. So it's H3C, so just make like an H, or no, sorry, I don't even need that. So it's H3C, right? So this is the carbon, and these are the 3 hydrogens. Okay. Now I'm gonna take this out, HO, make it into, so this would be O, H, and because of the octet rule, this would actually have 2 double bonds, so 1, 2, 3, 4, these bonds equal 4, and these 2 lone pairs would make it 8, and now this follows the octet rule. Okay, let's see, and if you can see for the nitrogen, it also does not follow the octet rule, because it has 2 bonds, 3 bonds, it has 3 bonds, but the thing is, nitrogen actually wants 3 bonds. Yeah, it wants 3 bonds, but it needs to follow the octet rule, which needs needs to make it 8, so just add a lone pair right here. Yep. Okay. Oh, also on the far left, this one does not follow the octet rule, so put 2 lone pairs right here, because then it would now have 8. And also for this oxygen, it has 2 bonds, but it doesn't follow the octet rule, so just add 2 lone pairs right here. Now you have 8. Okay, let me take the CH3 out and actually make it CH3. So CH3. 1, 2, 3. Okay, and then CH3. 1, 2, 3. Alright, now I'm going to find the. Actually, if you look at it, there's actually resonance. So I'm gonna remake this. Okay. So this nitrogen right here, it has a lone pair of 2. Or sorry, it has 1 lone pair. Actually, no. Sorry. That one does not work because the pi bond is not close enough. So what else can I do? Okay, I can do this one. This is a resonance. Lone pair right here. Make that 1. And then 2 right here. And then 3 right here. Between 2 and 3, there's a pi bond. And between 1 and 2, you make a pi bond. Let me show you. So make an arrow right here. That becomes a pi bond. And then the second bond on between 2 and 3. Sorry. Shit. Sorry. Okay. So this bond right here, it actually moves right here and becomes a lone pair. What else can I do? I can do this one too. This lone pair, 2 and 3, same thing. Move that lone pair right here. And this one, okay, this one actually, if you do valence electrons plus, valence electrons minus bonds, minus dots, you can actually figure out the, the formal charge for the oxygen. So before we actually move it, let me count this up. So oxygen, let me get my periodic table. Oxygen has 1, 2, 3, 4, 5, 6 valence electrons, and it has how many bonds? 2 bonds and 4 dots. So valence electrons, 6 minus 4. No, sorry, 2 bonds. 6 valence electrons minus 2 minus 4. Negative 2? No, that makes no sense. Well, to be honest, we don't really need to look at the charge for this problem. Okay. So between 2 and 3... Actually... Sorry, I drew the 2 and 3 wrong right here. It's not... Oh, no, I did it right. Okay. Sorry. Okay, so this bond goes right here. This is really messy, I'm sorry, but... You know what? I have a 2 and 3 right here. Okay. So... Yeah. These are... Okay, hold on. There's also... I forgot. There is a resonance right here as well. what did I just do? If you take this lone pair, why isn't it working? Lone pair, bring it right here, 1. And this is 2. So you make bringing between 1 and 2. Between 2 and 3 is a pi bond. Take this, move it up to 3. The oxygen still follows the octet rule, so you're good. Let's see. How do I go down? Okay, there we go. Now I'm gonna draw this again with the new, like, resonance and everything. And by the way, oh, wait, okay. Never mind. Okay. Oxygen. So this does not have 2 lone pairs anymore. It only has 1 because this has a pi bond because of the resonance. Okay. Let me draw this hexagon. Okay. Let me redraw this. It's terrible. Let me redraw this as well. These 2 lines are terrible. Okay. So yeah, now this one, it had a pi bond right here, but it doesn't anymore because the lone pair moved right here because of the the resonance. And right here there was a lone pair, or sorry, this becomes a pi bond now because the lone pair from the oxygen made it a pi bond, as I said before. This only has 1 lone pair. Okay, what can I do now? Alright. Lone pair right here. Okay. Sorry, there's a topo right here. Right, and this becomes a double bond because of the lone pair resonance, whatever. Oxygen. 1, 2, 3, 4, 5, 6. Let's see what else. Okay. I think that was the last of that was the last of the resonance. No more resonance. Actually, let me recheck the resonance. So if I do resonance right here, it'll just take you back to the original. If I do Okay. Well, as a matter of fact, I could do resonance. Either way, I could do resonance. Right here, I could do another resonance. You know what? Let me do that. Whatever. And yeah, let me just do that real quick. This is 1. Sorry, that looks like a 2. Let me redraw that. 1, 2, 3. Okay, so this basically moves here. Blah blah blah. This moves here. Kind of got the hang of this. Let me just draw it real quick instead of drawing the whole thing again. Saved in time. Take this out, take that out. Take the 3 out because I just told you. Okay, so I'm just gonna, to save time, I'm just gonna draw it instead of showing. Because, yeah. Shit. Okay, no, it's good. It's good. That line, I can't take it out. It doesn't mean anything. That little line right on the hexagon right there. It doesn't mean anything. I just can't take it out because it takes out the whole figure. But, yeah. Okay. So now, that looks really weird. Actually, whatever. It's okay. These two, I was just saying these two lone pairs together look weird, but just whatever. Alright. So now I'm going to draw or do the electron geometry for each, molecular geometry for each, and the hybridization for each atom besides the hydrogen. So let me just do this real quick. Can I find the colors? Okay, anywhere I highlight yellow is tetrahedral. I'm gonna write that down too. So this carbon atom right here is tetrahedral. Reason being is connected to 4 shared atoms and 0 lone pairs, which makes it 4 plus 0, which is 4. And no lone pairs doesn't make it a pyramid or whatever, you know. So it's just a simple tetrahedral. Right here. Okay, where else is there a tetrahedral? Let's start with the tetrahedrals. This one is a tetrahedral. You can't see it, but there's actually 2 hydrogen atoms connected to it, making it 4. Okay, this was a tetrahedral. 1, 2. This is a tetrahedral. This is a tetrahedral. This is a tetrahedral. Let's get those out of the way. This is not a tetrahedral. Neither is that. This is a tetrahedral. Let's see what else. This is a tetrahedral. This is a tetrahedral. Yeah. Okay. I think that's it for tetrahedrals. Let's see. Yep, that's it for the tetrahedrals. So let me write down what tetrahedral even, hybridization, whatever. So I'm gonna color code it yellow. Yellow equals, okay, electron geometry, molecular geometry, hybrid. Okay. So electron geometry for 4 is what? It's 109. Okay, 109. I think it's, yeah, it's 0.5, 109.5 degrees. The molecular geometry is, like we said, tetrahedral. And the hybridization. So SP1, P2, P3. This is SP3. Okay. Alright, now I'm going to do all the trigonal planars. And for that, I'm going to use using the color, let's see. I'm going to use green for trigonal planar. I'll say that later. Once I found all the trigonal planars, I'm going to state it too that this is green. So this is actually a trigonal planar because there's an invisible hydrogen. It's connected. It has 3 shared atoms, 0 lone pairs, making it a 3, and yeah, no lone pairs, whatever. What else? This is a trigonal planar. This right here, trigonal planar. Why did I do that? Why did I do that? Just do it like that. What else? This is also a trigonal planar. Mostly anywhere where you have double bonds, you most likely get a trigonal planar. So this is also a trigonal planar because there's invisible hydrogen and it has connecting 3, but it still has 4 bonds. The carbon wants 4 bonds, and it has 8 atoms. Yeah. And 2. This is same exact concept from the other green. I think that's it. For trigonal planar. I haven't gone to the lone pairs. I just ignored that for now. Sorry, this is also a trigonal planar because of the pi bond and because of the pi bond accounts for 2 bonds, and then the other 2 bonds are just connected to 1 atom. So you have 3 shared atoms but 4 bonds. So the formula is shared atoms plus lone pairs. 3 shared atoms, 0 lone pairs equals trigonal planar. Okay. What else? This is also a trigonal planar. Same exact concept like I just said. Let me redraw that. This is also a trigonal planar. You can actually see the triangle on that one. Actually, forget I said that. That makes no sense. Okay. Let's see. I think that's it. Yep. Let's see. Let me draw that right here. Equals electron geometry. Electron geometry for a trigonal planar is, or just the 3 is 120. Molecular geometry is trigonal planar. Like, yeah. And then hybridization is SP. So it's 3, right? So it's SV2. Yeah. Alright, what's left? We got an oxygen, 2 oxygens left, 2 carbon atoms with lone pairs. We got oxygen with 3 lone pairs. Wow, okay. And that's it? Okay, I can do that. Alright. So let's work with the 1 lone pair. Okay, let's just work with each atom now separately. So this atom, that one, the oxygen with 1 lone pair. So it has 2 shared atoms and 1 lone pair. So that's 3. Yeah, that's 3. And if on the Vesper table, it's a bent or angular. So that for anything that's bent or angular, I'm gonna make the color. What color can I do? I'm gonna make it blue. Bent or angular is blue. Okay. This is bent or angular. You know what? It looks like I'm crossing it out. Let me redraw that. Okay. Let's see. What else can I do? Okay, this is bent or angular too because 2 shared atoms, 1 lone pair. This one right here. And wait, that doesn't make any sense. Sorry, I got this one wrong. This is not bent or angular. This is actually 1, 2. So okay, let me look at it like this. There is an invisible hydrogen on this one right here. 2 shared atoms. So that makes it 3 and 1 lone pair. So that's trigonal pyramid. Because 3 shared atoms, 1 lone pair. Sorry about that. Okay, and that's the exact same thing. Wait, why am I drawing it blue? I'm sorry. God damn it. Okay, trigonal pyramid is actually going to be let me fix what I just did right now. Give me 1 second. Okay, trigonal pyramid, I'm just gonna make a different color. Trigonal pyramid is purple. This is trigonal pyramid. I'm gonna draw that out later on too. What else? Okay. So let's look at the oxygen. This oxygen down here, it's sharing. It's 2 shared atoms, or 2 bonded atoms. 1 lone pair. So that's 2 shared atoms, 1 lone pair. This is bent or angular. Bent or angular. Maybe try that. Bent or angular. Okay. else can I? Okay. Let me look at the oxygen up here. I think we got most of everything. This oxygen right here, it has 3 lone pairs, 1 bonded atom. So that is oh, that's not even on the Westford table. Confused. Oh wait, okay. So this is not on the Westford table. Let me look this up real quick. So this is 4, I know that, but I'm trying to find the correct Vesper table. Vesper table. Okay, it's linear, sorry. It's completely new, different color. Let's make this one red. This is red. Why do I keep doing that? This is red. Okay. So the colors that I forgot to write are blue, purple, and red. We said blue was... I said blue was... what did I say it was? I said it was bent or angular. So let me make a note on that. And write the electron geometry, whatever, is equals to... Sorry, what am I doing? Okay, I didn't get much sleep. So electron geometry, molecular geometry, hybridization. Okay, let's see. So I said the electron geometry. I didn't say that. I actually said it was bent or angular for molecular geometry. I'm gonna write bent. And for bent, it was 109.5. And since bent is 4, it is SP3. Okay. No, I got this one wrong. This is bent or angular, but this is 3, sorry. So this would be 120. Sorry. Bigger eraser. Okay, this is 120. And this is... I don't have to erase the whole thing. This is actually SP2. Sorry about that. Okay, and we have a purple. The purple was the purple was 3 shared atoms. So that's no, sorry. The purple was a lone pair. Okay. Two shared atoms, one lone pair. So that's bent or angular. Wait, what? I think I'm getting something wrong here. Let me skip that one for now. We said the red was linear. I said the red was linear. Red equals electron geometry, molecular geometry, hybridization. So linear. Okay. Let's see. $109, because this is 4. 109. And the one for 4 is SP3. Okay, let me fix. There's something wrong with my purple one. Matter of fact, I had it wrong. There is no such thing as whatever. This is actually blue. I don't know why I wrote purple. So I'm sorry about that. This is actually a double bond. No, wait. Is that a double bond or is that my? No, wait, that's a double bond. Yes. No, that's not a double bond. That's why I'm getting confused because handwriting is so terrible. I thought it was a double bond. This is a single bond, not a double bond. And there is a lone pair right here. Okay, 1, 2, 1, 2, 3. 3 shared atoms, 1 lone pair. 3 shared atoms, 1 lone pair. This is a trigonal pyramid. Yeah, this is a trigonal pyramid. These both are trigonal pyramids. Okay. Write that off to this side right here. Electron geometry, molecular geometry, hybridization. So trigonal pyramid is 109. Or sorry, that made no sense. Electron geometry is 109. Molecular geometry is that trigonal pyramid. And the hybridization is what? It is SP. Trigonal pyramid is 4, so it's SP3. Okay, now I just need to name the function groups. This is what it looks like now, right now. Now I'm going to name the function group. So let me start by circling every function group that is anything that is not CH or C single bond C or C single bond H. So this is C double bond C, so that might work. This is definitely has to be something. I don't know what, but I guess we'll find out. This probably is something. This is probably something. I usually like to just circle everything, but then I find out it's not a function group, so then I erase it at the end. This definitely has to be something. This is a ketone, I can just tell by looking at it. This is also probably a ketone. This would be an arene, but it's not because I screwed around with it because of the resonance. So because of the resonance, it's not an arene. Okay, let me look at my function loops real quick. So, like I said, this was a ketone. This is also a ketone because C double bond O makes a ketone. And C single bond O, now that I'm looking at it, there is absolutely nothing. There was before. This could have been a amide right here, but I can't do it anymore because of the resonance. But this whole thing could have been an amide if we never made the resonance. But yeah, it's not. Not anymore, at least. Actually, yeah, it's not anymore. So this is an amine. Actually, amine. This right here. I'm just gonna erase this because yeah, because it's no longer an amide or whatever. Like I said. So C double bond C, that's an alkene. This is an alkene. Alkene. Yep, that's it. This is question number 1. Finished. This is what it looks like. If I zoom out on this thing. What the hell? Okay, yeah. This is what it looks like complete. Oh, wait. Sorry. N double bond C, is that something? This is a nitrile. This right here. This is a nitrile. Sorry, I forgot to mention that. Now this is complete. Okay.